maybe a little late doing this filming, because I prefer the day. So switch on the light, and hence the cap. Okay, so here's your formal description of BI. Remember, it's the automaton that recognizes the language, AI. And what's AI? It's the language whose strings, set of strings, and the strings are such that if you sum all the zeros, ones and twos in the input string, you'll get a sum that is a multiple of I. Right? So the states, now we have, so the Q, now the set of states, capital Q, now that's going to depend on what I is. So here's your set of states, okay? And we have I of them, and start state Q0, so that hasn't changed, and the capital F, the set of accept states, is just the set of Q0. So that's pretty similar to, this whole exercise is like a generalization of the previous one that was running some mod 3, or the language set of input strings whose sum is a multiple of 3. In this case, this is a multiple of I. Right? Now the hard part is the transition function. So all those rules that decide when you switch from one state to the next. So here are the specification, the description, definition of your transition functions, your deltas, that would make this a summer mod I. Okay. So for each j in this list, ranging from 0, 1, 2, okay. So if your automaton BI, if it's in the state Qj, then you've got to be one of these states. Right? But how many of them? I. You've got I of them. Right? So you specify an I, some arbitrary positive integer I, and then you're designing BI. You're designing an automaton that would recognize the language AI. Okay. So if your automaton's in some state Qj, one of these, right? And what is that Qj? Well, it's the running sum so far. You're running, meaning the sum that you have at the moment as you're reading present tense, as you're reading through the input string, right? That's what they say running. It means sort of like flowing, not finished yet, sort of. Okay. So the running sum is j. So if your running sum so far is j, you're in state Qj. That's sort of important. Okay? Mod I, of course. Okay. So so for any state Qj, whatever it is, whatever this sum is, mod I. Now, if you add 0 to it, well, it won't change, right? So the running sum Qj should be the same. If you add 0 to it, it doesn't change anything. So if you're in this state and this is your input symbol in the string, well, you don't change the state. You just stay there. Okay. Now, similar logic. So if you're in this state, in other words, that's your running sum. Your running sum is j, and the input symbol is 1. So you add 1 to this. So so the running sum should now become Qj plus 1. Okay, but you need to mod it by I. I mean, it could be j is, it could happen that j is equal to I minus 1, right? And then you add 1 to it, so you've got I minus 1 plus 1, that's I. Well, if you mod it with I, you get 0. So you need to mod it, right? So take your qj, add 1 to it, and then mod it I, and then the result will be, call that qk, okay? Where now k is equal to j plus 1 mod I. Hope you follow that, okay? So you're choosing, in other words, you're choosing your transition rules, your deltas, such that this automaton is adding each time it sees a symbol, it's adding 0 or 1 or 2 to the running sum and modding by I, mod I. Okay. Now, if you add 2, you'll get another state, like you'll j plus 2 and mod I, and whatever the result is, that's n. So you'll go to state qn, corresponding to this number here, right? And if you're in state q, whatever it is, for any q, j, if you're in state j, and then you read reset, thinking of reset as a symbol, then you go to state 0. So this q0 corresponds to the number, the running sum, 0. Right? Reset just means put it back to 0. Okay, so that's the end of the analysis of the example 115. Right? Okay, now so we can now give a formal definition of what's going on when you compute. Now we've sort of done it quite a few times already informally, but now we're going to make it formal, sort of more mathematical. So we've been describing a finite automata informally using the state diagram, state transition diagram. Okay, and formally with the 5 tuple, like here, using the formal definition, using the 5 tuple. Now, so staying here, it's usually easier to analyze, to think about the state diagram, okay, because it's sort of visual and it's usually smallish number of states and so forth. Okay, but but the formal definition is it's more precise and it's good for disambiguation. Familiar with that term? To disambiguate. It means to get rid of the ambiguities, things that are not clear. Now how do you interpret that? Does that mean this or does it mean that? Right? So the formal definition is good for getting rid of that doubt. Is it this or is it that? How to interpret it? So disambiguation is getting rid of the ambiguities, so it's clear what the meaning is. Okay. So the next session we will give a formal definition, sort of math type definition of how an automaton computes. How now you'll find this familiar because we've done it already several times, but it's just sort of written out in a more precise sort of mathematical way of what happens when we use an automaton to compute. And what does that mean actually? Well, to recognize a language or to accept or reject a specific input stream. Okay, so we'll just follow on this on the next session.